Welcome back. In this video, we're going to start chapter 4, which is about systems of linear equations. As always, when we start a chapter, it's a good idea to look ahead, see what it is that we're getting into before we get into it. So this chapter, it says the title is Systems of Linear Equations. There are a total of 7 sections in the chapter. We're only going to go through 4.1 through 4.4 and 4.7. Sections 4.5 and 4.6 cover content that is often covered in a college algebra course, and so it's not really within our scope here. So section 4.1, it says solve systems of linear equations with 2 variables. So whatever a system of linear equation with 2 variables is, we're going to solve those. And then section 4.2, it says solve applications with systems of equations. So section 4.1 is going to cover a lot about what is a system of equations, what is a solution, how do you find those solutions, and so forth. Section 4.2 kind of applies all of that 4.1 stuff to story problems. And then it gets more specific from there. Section 4.3 is about mixture problems, which we have done mixture problems before, but it turns out you can use systems of equations to solve those. Section 4.3 goes into how that's done. Section 4.4 is about systems of equations with 3 variables. So 4.1 will be systems, and 4.2 and 4.3 is all systems of 2 equations with 2 variables like x and y in it. Section 4.4 extends those ideas to sets of 3 equations with 3 unknowns in it. And then finally, section 4.7 is about systems of linear inequalities. And recently we went over how to graph a linear inequality. That was where you graphed a line, and sometimes it was dashed, sometimes it was solid, and then performed a little test and shaded one side or the other. So it's going to be kind of like that, only a little different. So that's where the chapter will finish. The probably most new concepts kind of for the section for the chapter will be in section 4.1. After that, it gets into applications and then an extension to more different variables. So let's get started with section 4.1. This is going to be one of those topics where you've, in all likelihood, seen this before, but we're going to pass over a lot of things more or less kind of quickly. So make sure that you are also reading the textbook in conjunction with watching the lectures here. All right, so systems of linear equations with 2 variables. What one of those is a grouping of 2 or more linear equations like what you see here, 3x plus y equals 0 and x plus 2y equals -5. So here, linear equations with 2 variables. The part about it being 2 variables should be obvious. It's just x's and y's. What makes them linear equations is that in here you don't see any x squareds or square roots of x's or 1 over x's, nothing like that. All of the equations can be made to look like ax plus by equals c, where the exponents on the 2 variables are just 1s. So they are linear equations. So for throughout this video, I'm just going to end up saying system of equations instead of saying system of linear equations in 2 variables, just to make it shorter and easier to listen to. So keep that in mind whenever I say system of equations in this video, that system of linear equations in 2 variables, okay? All right, so what our goal is in this section is to find those solutions to a system of equations. A system of equations, the solution is an ordered pair, x comma y inside of parentheses. So for example, for this system, 3x plus y equals 0 and x plus 2y equals 5, equals -5 rather, we want to check and see if the point 2,4 and the point 1, -3 are solutions. All right, so how we can do this. All right, sorry about that. Zoom crashed on me. So once again, what we're going to do is check and see if these 2 ordered pairs are solutions to this system or not. So here, we're going to check first 2, 4. So remember that the values are in order in an ordered pair. So the first one is the x, the second one is the y. We'll replace the x and y in the equations with those values and see what we get. So for the first one, we have 3x plus y equals 0. I'm going to replace the x with a 2 and the y with a 4. And we get 6 plus 4 equals 0, and that's 10 equals 0, and that's false. So the ordered pair doesn't even satisfy the first equation, and so we don't even actually have to check the second one. So the first ordered pair is not a solution to the system of equations. Let's check the second pair. So we're going to check 1, negative 3 next. 3 times 1 plus negative 3. We want to know if that is 0. 3 plus negative 3 is in fact 0. So the first equation checks out. We have to make sure that that xy pair fits the second equation as well. So we'll have x plus 2y equals negative 5. Here x is 1, and then we have 2 times negative 3 equals negative 5. 1 plus negative 6 does equal negative 5, so that works out. Since the x and y values in that ordered pair fit that both equations, we have a solution to the system of equations. Okay, so our goal in this section, as I said, is find those solutions to those systems. It's important to note that for a system of linear equations, we can always consider the graphs of these in the xy plane. And we've practiced with graphs quite a bit, and so we could talk about what's possible. If we graph the two linear equations in a system, there are three possibilities. Either the two lines intersect in a single point, in which case the point where those two lines intersect is our solution. That xy pair is a solution to each of the two linear equations. In that case, we'd say that there's a consistent system and the equations are independent. The other possibilities are, first of all, that the two lines are parallel, and so they never intersect, parallel and non-intersecting. In that case, there's no solution. There's no xy pair that satisfies both of those equations at the same time. In that case, the system is inconsistent. The equations, however, are independent. It could be that the two lines actually are on top of each other when you graph them. When that happens, there are infinitely many solutions, in which case you'd say there are dependent equations and the system is inconsistent. Of course, the most exciting one is where we get just one and only one solution, but we have to make sure we pay attention to the other two cases as well. One way of solving these systems of equations is by graphing. So you can go ahead and graph the two equations and see what we get. We're going to try that with this one. Here we have x minus 3y is negative 3, and x plus y is 5. So both of these equations are in general form. So I'm going to do this by finding their intercepts. So for the first equation, when x is 0, y will be 1. And then when y is 0, x will be negative 3. So let's go ahead and draw that. So we have the point 0, 1 and the point negative 3, 0 on our graph. So let's go ahead and draw that line. And then we should do the next one next. X plus y equals 5. When x is 0, y is 5. And then when y is 0, x is 5. So we'll have the point 0, 5 and 5, 0. And then once again, we're going to connect the dots. And you can see that the two lines intersected in this single point. So let me just circle that. So it looks like they intersect at the point 3, 2. So what we've done here is we've solved the system of equations by graphing, and there's some advantages and some disadvantages to doing it this way. First, the advantages. The advantage, really only one, is that it makes it easy to visualize what's going on with the system of equations. We can tell on this one that it's a consistent system and the equations are independent. There's exactly one solution for this. When we're solving a system of equations, we're looking for that xy pair, if any, that satisfies both of the equations. So in short, the value of doing this by graphing is visualization. The downsides, and there are a couple, are first of all the time intensiveness of it. It takes a little time to do the graphing. Secondly, if you don't like graphing, you probably won't like this because you're graphing two lines. And then thirdly, the quality of your answer depends on how good your graph is. Here, the problem is, of course, carefully chosen to work out nicely. But looking at the picture here, I'm just kind of assuming that it's going to be 3.2, but I guess it could just as well have been maybe 3.01 and maybe 1.99. And you wouldn't know based on the picture, right? How good the answer is depends on how good the picture is. And so that's a disadvantage. Of course, in math class, a lot of times the answers are kind of carefully chosen to work out real nice, but that's not always the case. And here the lines themselves were pretty easy to graph. So I'd recommend solving one or two of these by graphing, just to get a feel for it, and then thereafter we have better ways of doing it. And so we want to look at those better ways right now. So the first method we have is solving by substitution. There's going to be two ways we'll have, aside from graphing: substitution and elimination. We're going to do substitution first. So for this one, we have negative 2x plus y is 11, and x plus 3y is 9. So what we'll do is we'll take the first equation, negative 2x plus y equals 11, and solve it for y. So I'm choosing y, by the way, because its coefficient is 1. That's going to make it easier. So y will equal 2x plus 11. Now we know what y is. It's 2x plus 11. We're going to substitute that, which is why it's called this method, into the second equation. The second equation is x plus 3y equals 9. I've left parentheses and a little gap in there to replace y with what it is, and what it is 2x plus 11. You'll notice now, after doing the substitution, that we've just ended up with an equation with one variable in it. And luckily, we've had a lot of practice at solving those. So I should be able to get this done. So that's 9 minus 33, that's 20. Sorry, I'm getting ahead of myself. All right, so I just wanted to double check and ensure that I was doing that right, because it seemed kind of weird that I was getting negative 24/7. Like I was saying a few minutes ago, solving these by graphing, our answer's accuracy would have depended on how good our picture was. And I don't think I could ever draw one of these well enough that I could find that the answer was 24/7. But that looks like what we get according to the algebra. Once we've got the value for x, we can substitute this back into either equation and calculate the corresponding value for y. So here I'll go back to the 2x plus 11 one. Y is 2x plus 11. And then we have a little bit of arithmetic to do. So this is negative 48 sevenths plus 77 sevenths. And then we need 77 minus 48. That looks like 29 sevenths. Okay, so our xy pair then would be negative 24 sevenths and 29 sevenths. So that's the basics for how it works to solve by substitution. In this example, we first took the first equation and solved it for y. We could just as well have solved it for x if we had done that, which I wouldn't recommend, but had we done that, we would have had negative 2x is equal to minus y plus 11, and then dividing through by the negative 2, we'd have minus y plus 11 over negative 2. And then you would probably find the calculations there more cumbersome, so more difficult. So that's the reason why we would avoid that. It would have been about the same level of difficulty if we had taken the second equation and solved it for x instead. So we could make x be negative y plus 9 and replace that into the first equation. So negative 2x plus y equals 11. And then our x was negative 3y plus 9. Okay, and then I'll leave it to you to go through the details there, but we would have ended up with the same answer. All right, so here's one for you to try. Take a minute, pause the video, and then try this one, and then restart the video and see how you did. So there's one good choice here, and then a couple of bad choices. So try to make a good choice at the beginning, then we'll see how you did. All right, let's see how this has gone. So we're going to take the first equation and solve for y. So we'll have y equals 4x for the first equation. That's relatively nice. We're going to take the second equation, 2x minus 3y equals 5, and I'll replace that y with the 4x. So now we'll have 2x minus 12x equals 5. So negative 10x equals 5. X is negative 5/10, which is the same as negative 1/2. Okay, once we've got the value for x, we will back substitute into a equation to get y. And it doesn't matter which one you substitute into, so I would choose the one that's easiest. I think the y equals 4x one is easiest. So we'll have y equals 4 times negative 1/2, and that will be negative 2. So we'll have negative 1/2 for x and negative 2 for y. And that will be our solution. Okay, next up, we want to take a look at solutions by elimination. So first of all, why is it that we need two methods? While you could technically do any problem with either method, sometimes some problems are just easier done with one method or the other. In the last example we did, it was not too bad because the second or first equation had a coefficient of negative 1 in front of it. If we had a problem like 3x plus 8y plus 19, negative 4x plus 12y is 21. For this one, the coefficients of the variables are all not 1. So no matter which variable you pick in which equation, you're going to end up with fractions involved, like 19/8 or 21/4 or something. So neither of these, or there's no good choice really to do this by substitution. So elimination might be helpful. So that's why we have two methods. So first of all, the basis for how elimination works. So, and then we'll see some examples. So let's say that you have a system of equations where the overall structure is A equals B and C equals D. So first of all, if you have two things that are equal to each other, one of the things that we know is we can add the same amount to both sides. We use that to help us solve equations like 2x minus 3 equals 10. How you would solve that is by adding 3 to both sides, right? It's always okay to add the same amount to both sides. So I'll take my equation A equal B, and we're going to add C to both sides. Okay, we're allowed to do that, right? In the same way that we would add 3 to this 2x minus 3 equals 10. The second thing is we know that equals can be replaced by equals. So when I rewrite this equation, A plus C equals B plus C, I'm going to take the second C and replace it with a D. How do I know this? Well, we're told that C and D are the same, so I can replace this upper C with a D. All right, so from there, taking a look, we've got A plus C equals B plus D. And so what this kind of justifies is that if we add together the left sides of two equations and the right sides of two equations, then we get a true equation. And if we do this carefully, we can eliminate a variable. For example, if we had x plus y equals 10 and x minus y equals 4, if we added together the two equations, we get 2x, y plus minus y is no y's, and this would give us 14, so that x would be 7. You'll notice here that the y is eliminated. That's how this method works. Let's go ahead and finish that one since I started it. Once we know that x is 7, we can back substitute into an equation to solve for the other variables. So in this case, the y has to equal 3. So we'd have 7, 3. This one, on the face of it, it doesn't look like it's so easy, because if we just add together the two equations, 3x plus 2x is 5x, y plus negative 3y is negative 2y, and then we'd have 12. We didn't get a variable to be eliminated. So the kind of pre-step that we're going to need to do is to multiply one of the equations, or maybe both, by some number to make it so that the variable will be eliminated. Here, 2 and 3, we could multiply one or both of these actually so that they're 6 and negative 6, but it's actually going to be easier to multiply the first equation by 3. So let's do that, and you'll see how nice it works. We're going to multiply the first equation by 3. Now I like to make a little note to myself so that I remember what I did in case I have to go back and check. So we're multiplying by 3. This will give us 9x plus 3y is 15. Keeping the second equation the same, we'll have 2x minus 3y is 7. Now when we add together the two equations, we'll have 11x. 3y and minus 3y is no y's. On the right side, 15 and 7 is 22. If 11x is 22, then x has to be 2. So here we've scaled, by multiplying by 2, we scaled the first, multiplying by 3. We multiplied the first equation by 3. That made it so we're able to eliminate a variable. Once we've done that and found, in this case, that the x is 2, we'd have to substitute into one of the earlier equations to find the value for y. It doesn't matter which you choose, so I would choose whichever one is going to seem easiest. I think the first one, 3x plus y equal 5, will be best. So we'll have 3 times 2 plus y equals 5. 3 times 2 is 6. 6 plus y equals 5. That's going to mean that y has to be negative 1. So our pair is going to be 2, negative 1. All right, here's one for you to try. This one has got fractions in it, but that's okay. What I would do is take a hint from the last problem where we multiplied by 3 and think about how you can use that to maybe get rid of those fractions. So take a minute, pause the video, try to solve this one yourself, and restart the video and see how you did. All right, so we're back. So here we've got denominators of 3 and 2 in the first equation and 4 and 2 in the second equation. What we're going to do first is multiply to clear the fractions out of both equations. For the first one, the denominators are 3 and 2. The least common multiple of 3 and 2 is 6. So we're going to multiply through by 6. So 1/3 x times 6 will be 2x. And then a half of y multiplied by 6 will be 3y. On the right side, don't forget to multiply that also by 6. We'll just have 6. For the second equation, the least common multiple of 4 and 2 is 4. So we're going to multiply by 4. Okay, so then 3/4 times 4 will be 3. So we'll have 3x. And then we'll have minus 4y. And then 4 times 5/2 is going to be 10. All right, so we've succeeded in getting rid of the fractions, but now notice that if we add together the equations, we won't get a variable to eliminate still. And on this one, the signs of the x coefficients and the signs of the y coefficients are the same, so there isn't an obvious choice. So you could do either one. So here we could multiply the equations by 3 and negative 2 and eliminate x's by kind of building up the coefficients of x to be 6 and negative 6. Or we can make the coefficients of y be 12 and negative 12. It's totally up to you which one you choose. I think I'm going to go with the first one just because I'm multiplying by maybe smaller numbers. So let's do that. So the first equation here is going to get multiplied by 3. This will give us 6x minus 9y equals 18. And then the second one, I needed to make it so that these x's cancel. So I'm going to multiply by negative 2. So we'll have negative 6x plus 8y. And then that's negative 20. Now the coefficients of x are opposites, and so when we add together the equations, the x's will vanish. We have negative 9y plus 8y will give negative 1y, and that's equal to negative 2. That means the y has to be 2. Now that we know y, we can go back to any equation that has both x's and y's to get our value for x. It doesn't matter which we choose. I think I'll go with this one because it's nearby. 3x minus 4y is 10. We'll have 3x minus 8 is 10. 3x is 18, so that x is 6. So we'll have 6, 2. So on this one, to summarize, we multiplied first by some carefully chosen numbers to eliminate the fractions, and then we had to multiply again in order to make the coefficients of x be opposites, and then we were able to solve for one variable, back substituted to get the value for the other variable. Okay, I realize this video has come out kind of long, but we're almost there. We just have one more set of 2 examples involving some special cases. Regardless of whether you are using substitution or elimination, there are a couple of special things that can happen. And so that's what these 2 examples illustrate, and then we're done. Okay, so this one, I've kind of set it up so that it's ideal for substitution. So we're going to use substitution to solve for it. Although if you want, we can multiply through by 4 to clear the fractions out. But let's just actually do substitution right in. So 3x plus 4y. And here y is 3 minus 4x. That's equal to 12. Okay, so I've substituted, and that eliminated the y's. We have just x's in our equation. We'll have 3x plus 12 minus 3x equals 12. 3x and minus 3x add to 0, and we have 12 equals 12. When you end up with a statement like that that is always true and no more variables are in it, then that is the case where you have the infinitely many solutions. If you graph the 2 lines, they're going to lie exactly on top of each other. Okay, that is the consistent system dependent equations case. So this one has infinitely many solutions. Okay. Let's try the next one. Here we have y is 2x minus 1, 8x minus 4y is negative 12. So again, I'm going to use substitution for this because it's kind of set up for substitution. So we have 8x minus 4y is negative 12. Our y is 2x minus 1. That's 8x minus 8x plus 4 equals negative 12. Here again, the x's vanish, but this time we have 4 equals negative 12, and that's always false. When you have a situation like that where the variables all go away and you get something false, then that means that there's no solution. Or you've made a mistake, but probably what has happened is that there's no solution. Okay, if you graph these, you're going to end up with 2 parallel lines that don't intersect. Okay, so that takes us to the end of section 4.1. Just to kind of quickly recap, we saw what a system of equations was like, what the solutions are like, and how you can solve the systems using either elimination or substitution or graphing if you really have to. And we saw that if you end up with a situation where the variables all go away and you end up with something that's always true, then that means that there's infinitely many solutions. If you end up with a situation where it's always false, then that means that there are no solutions. Okay, that takes us, like I said, to the end. Let me know if you have any questions, and have a great day.